So there's another construction we can do to make a subspace whenever we've got a couple elements of a vector space. So we'll take two elements, u and v, and then we'll take the collection of all linear combinations of those two guys. This will form a subspace of v called the span of u and v. So the span of u and v is all elements of v such that they are a linear combination of u and v. Okay, so let's see why this is a subspace. Well, first off, it's clear that 0 is always going to be in the span of a couple of vectors, because if I take a and b both to equal 0, then I get that 0 is equal to 0u plus 0v. So we know that it contains the origin. All right, what about sums? So suppose we take, let x and y both be elements of the span of these two vectors. Okay, well, actually here, let's tell you what, let's do this. Let's give them numbers. Let's let x1 and x2 both be elements of the span of u and v. Okay, so what does that mean? So we write down the definition. Okay, so we go back to the criterion for membership, and it's that you have to be a linear combination. So we'll say x1 looks like a1u plus b1v. And since x2 is also an element of this span, x2 is going to be a2u plus b2v. Okay, so then what about the sum? If I look at x1 plus x2, then this is going to be, well, x1 we figured out was a1u plus b1v, and x2 was a2u plus b2v. And that's by our choice of picking these guys in v. In other words, I'm just saying I'm using this and this data right here in this next step. So I can collect now the u terms and the v terms, and now I have a linear combination of u and v. So this shows that x1 plus x2 is a linear combination of u and v, and I've got my coefficients. There's here's the first there's the coefficient of u, and there's the coefficient of v. Okay, what about scalar multiples? If I look at cx1, this is going to be c times a1u plus b1v. And so I can distribute the c, and I get c a1u plus c b1v. And so now again, I've got a linear combination of u and v. There's the coefficient for u. There's the coefficient for v. So this guy's back in v as well. So it's closed under each of these. So one way of thinking of the span of two vectors u and v, and it's sort of a nice picture to draw, is to think of what happens if v is R3. So this is in the case when v is R3. Then what we're doing is we're saying, okay, I'm going to pick some vector u and some other vector v, and then I'm going to look at all linear combinations of these two vectors. So that gets me to any point on this plane. Right? So, for instance, if I take half of a u and 3/2 of a u and half of a v, and add those together, then that'll get me out to this point right here. So that's an example of a linear combination. Okay, and that's a very nice visual way to think about it, but we've also seen examples of this before. So, for example, say our vector space is solutions to this differential equation, this homogeneous linear differential equation of order 2. Well, then we know that if we take y1 to be cosine 2x and y2 to be sine of 2x, then both of these are elements of this vector space. And so now the span of y1 and y2 is going to be all functions of the form y equals a cosine 2x plus b sine 2x. And you can check that that is a vector space, and in fact it is the solution space for this vector space of functions.